In this lecture video, we're going to make the switch from working with independent samples to working with dependent samples. There's some notation that we're going to need to be able to use correctly in order to do this type of hypothesis test or confidence interval. D represents the individual difference between the two values in a single matched pair. When two samples are dependent or consists of matched pairs, the sample values are matched up and the matching is based on some inherent relationship. And we can find the difference between each individual data value and its matched pair from the other sample. Mu sub D is the mean value of the differences D for the population of all matched pairs of data, while D bar is the mean value of the differences D for the paired sample data. S sub D, that's the standard deviation of the differences D for the paired sample data, and N is the number of pairs in the sample data. Let's take a look at the requirements. It's required that the sample data are dependent or consist of matched pairs. The samples need to be simple random samples, and either one or both of these conditions must be satisfied. The number of pairs needs to be large, that is, N needs to be greater than 30, or the pairs of values have differences that are approximately normal. Once these requirements are met, we can run a hypothesis test or construct the appropriate confidence interval. For a hypothesis test regarding two dependent samples, our test statistic is a t-statistic, and it's calculated like this. Notice what we have in this equation. We have D bar, that's the mean of the differences of the sample data. We have mu sub D, that's the mean of the differences from the population. And that value will be found in the null hypothesis. We have S sub D, the sample standard deviation of the differences, and N, the number of pairs. Thankfully, we can use our calculators to calculate this test statistic and run the hypothesis test. The calculator function that we will use for this type of hypothesis test is t-test. We'll need to put our data values into lists. We'll put one set into list 1 and another set into list 2. Then we'll define a third list equal to the difference between the two lists. And we'll need to make sure that we enter our values into the two lists so that our data values are matched appropriately. We can also construct a confidence interval. To do that, we start with D bar. Since D bar is the mean of the differences for the paired sample data, that's our best point estimate. And we can find our interval by adding on and subtracting off the margin of error. That is, we believe that mu sub D, the mean value of the differences for the population of all matched pairs of data, is between our best point estimate, D bar minus E, and D bar plus E, where E, the margin of error, is equal to T sub alpha over 2 times the standard deviation of the differences for the paired sample data over the square root of the number of pairs. We can also use our calculator to find this confidence interval. The calculator function we'll need is called t-interval. And again, we will need to put our values into lists and construct a third list defined to be the difference of the other two. Let's take a look at an example. Listed below are the ages of actors and actresses at the time that they won Oscars for the categories of Best Actress and Best Actor. The data is matched according to the year that they won. Use a 0.05 significance level to test the claim that this paired sample data comes from a population for which the mean difference is 0. In other words, the claim is that there is no significant difference in this paired sample data. There's no significant difference between the ages of actresses and actors at the time they won their Oscar. We can express this claim as mu sub D equals 0, and we are told to use a 0.05 significance level, so that's our value for alpha. We will need to build lists for our data. Let's let the actresses be our first sample, and we'll put those values into list 1. We'll let our actors be our second sample, and we'll put those values into list 2. We will then need to build list 3 equal to list 1 minus list 2. Let's get started with that part before we conduct the hypothesis test. We will first go to Stat and Edit, and make sure your lists are cleared before you begin. You don't want any stray data values affecting your hypothesis test. So in list 1, we'll enter the ages for the actresses. And in list 2, we'll have the ages of actors. It's important that we enter them in order so that when we find the difference, we're finding the differences for paired values. Now it's time to build our list 3. With list 3 highlighted, we'll type list 1 by pressing second 1 minus list 2 by pressing second 2. Pressing enter will populate list 3 with the differences of each value from list 1 and list 2. Now that our lists are set up, let's head back to the example and get ready for the hypothesis test. The first step is to determine the null and alternative hypotheses. The null hypothesis is the statement of equality that mu sub d is equal to 0. That's the idea that there's no significant difference. Notice that in this example, the null hypothesis matches up with the claim. That means the alternative hypothesis, H1, will be the idea that there is a significant difference, that mu sub d is not equal to 0. The second step is to calculate the test statistic, and we can do that with our calculator function. Heading back to our calculator, this time we're going to go to Stat, Tests, and go to option 2 for t-test. We have the individual data values, so we're going to select data and press enter to highlight it. Mu naught, that's the value that comes from the null hypothesis. In this case, that would be 0 because the null hypothesis states that mu sub d is equal to 0. For the list, we need to enter the list that has the differences. In this example, we put that into list 3. Leave the frequency as 1 and select the correct option that matches the alternative hypothesis. Our alternative hypothesis is that mu sub d is not equal to 0. So we want to select enter while not equals mu naught is highlighted. Finally, while calculate is highlighted, we'll press enter. This gives us a test statistic of negative 1.507. It also gives us our p-value of 0.2063. Let's take that back to our example. We found our test statistic to be t equals negative 1.507. Our calculator also gave us information about the p-value. We found our p-value to be 0.2063. If we instead use the critical value method, we would need to find the test statistic t that corresponds to this value of alpha in a degrees of freedom equal to 5 minus 1, or 4. Since this is a two-tailed test, we would have two test statistics, t equal to plus or minus 2.776. Now we can state the conclusion. Comparing our p-value to alpha, we find that our p-value is significantly greater than alpha, which means that we fail to reject the null. In this instance, the null is our claim. So in other words, we fail to reject the claim. We cannot definitively support the claim, but this sample data does not throw that claim out. It does not reject it. So we could say something like this. There is not sufficient evidence to reject the claim that there is not a significant difference between the ages of actors and actresses. Looking at this through a lens of practicality and common sense, though, it might lead us to somewhat support the claim. Let's take a look at another example. In this example, we're going to test a claim by using a confidence interval. Researchers collected data on the number of hospital admissions resulting from motor vehicle crashes, and the results are given below for Fridays on the 6th of the month and Fridays on the 13th of the same month. Construct a 95% confidence interval estimate of the mean of the population of differences between hospital admissions on the days that are Friday the 6th of a month and days that are Friday the 13th of a month. Use the confidence interval to test the claim that when the 13th day of a month falls on a Friday, the number of hospital admissions from motor vehicle crashes are not affected. In this situation, our data is paired or matched up by month. These pairs of data represent months where the 13th landed on a Friday, which would necessarily mean that the prior Friday was the 6th of the month. We'll put our Friday the 6th values in list 1, and we'll put our Friday the 13th values into list 2. We'll then build list 3 equal to list 1 minus list 2, the differences between each pair of matched data. The claim here is that the number of hospital admissions is not affected, that there really isn't a significant difference, or that the mean of the differences is equal to 0. We also need to use a significance level of 0.05. And we know that because we're constructing a 95% confidence interval estimate. That leaves 5% or 0.05 left over for alpha. We're going to use our calculator, and the function that we're going to use is t-interval. Let's get started. The first step is to put our data into our lists, and we start by clearing out any old data. We'll enter our values for Friday the 6th into list 1. And we'll enter our values for Friday the 13th into list 2. Finally, we'll build list 3 as the values from list 1 minus the values in list 2. Now we're ready to construct our confidence interval. We need the function t-interval, which can be found by going to Stat, toggling over to Test, and scrolling down to option 8, t-interval. We have our raw data. So we'll make sure that data is selected. And our differences are found in list 3. We'll leave the frequency at 1 and adjust our confidence level to 0.95. Pressing enter while calculate is highlighted will construct our confidence interval. Here our confidence interval is negative 6.493 to negative 0.1734. Since the original data values are rounded to no decimal places, we'll go ahead and round to 1 decimal place. We have a confidence interval of negative 6.5 to negative 0.2. So we could write a concluding statement of we are 95% confident that the interval from negative 6.5 to negative 0.2 contains the actual mean of the differences mu d. What do we notice about this interval? This interval does not contain 0, which implies a difference between the two populations, and the values are all negative, which implies that mu sub d is less than 0. And if mu sub d is less than 0, that would mean that the mean values from list 1 minus list 2 is less than 0. Allow me to write this in an interesting way. We have the values from the 6th minus the values from the 13th are less than 0. In other words, we found that the values from the 6th are less than the values from the 13th. That implies that there are more accidents on Friday the 13th resulting in hospital admissions than Friday the 6th. So what do we do with the claim? We reject the claim. We have evidence to believe that there is a significant difference, not that the difference is 0. We are done with this example, but I do want to point out one small detail. Notice that our confidence interval is very close to containing 0. It is just barely underneath it by 0.2. So if we would have used a higher confidence level, this interval would contain 0 and we would not reject the claim. We would say that it is possible that there is not a significant difference. So in other words, the level of significance chosen does make a difference in our conclusion, and it's important to take note of such details when you're doing your own research. That concludes this lecture video on how to conduct a hypothesis test or construct a confidence interval for 2 dependent samples.